Anyone? Oh, Whitney's typing. Okay, good. We are going to spend a large bulk of our time here on page 689 on the fundamental figure 2019. So if you have your book, this would be a great thing to look at, or you can just look at me and my green arrow. Haha, there. Okay, so the main part and the main thrust really of this whole chapter is, besides understanding the anatomy of the heart and how the heart muscle, cardiac muscle, functions a little bit differently than skeletal or smooth muscle, is to understand how it all relates as far as pressure and volume and heart sounds and electrical activity and valves opening and closing and why that's important. And that's what we call the cardiac cycle. And the cardiac cycle is typically defined as the activity from one heartbeat to the beginning of the next heartbeat. So we're talking about, we often talk about the fact that the heartbeat sounds like lub-dub. So you're looking at one lub to the next lub. And in the 9th edition, this particular diagram is shifted a little bit. So sometimes it's a little harder to try to really see a true cardiac cycle. Here, in the 10th edition, they made it a little bit clearer, starting it with they kind of split phase 1 into 2 different phases, which I'll talk about in a minute. But it does give you a little bit better idea of what's happening as far as ECG and heart sounds and so forth. So if you have the 9th edition, I have attached the 10th edition diagram, this one, in the notes from instructor, so you can pull that down if you find it easier. Most students do. If you have the 10th edition, then you do have the correct and clearer version. So your text divides the cardiac cycle into 5 phases. Other texts and other resources, if you go online, will divide it into 4 phases. And the only difference in your text is that the active ventricular filling and the passive ventricular filling is used as one phase. And so when you're going through other resources, because I know a lot of you do, just keep that in mind. If you see 4 phases, it's just because they do passive and then active at the end of that phase rather than as a separate phase. Your text uses them as different phases because of the way they've done this diagram. If they did it as one, it would be essentially saying 1B, 2, 3, 4, 1A. And that seems a little weird to start a diagram with 1B, and I think that's probably why they split it into 5. But like I said, it just depends on what resources you're using, what textbook. As some of you may have discovered, especially if you're in lab, not all veins and arteries are highlighted the same. And we talked a little bit about that last week, that some places and some resources highlight oxygenated versus deoxygenated. So oxygenated are pink or red, and deoxygenated are blue. Other resources do all arteries as red and all veins as blue, whether or not oxygenation is happening in the blood inside those vessels. And so you just have to really pay attention to the source, and I know that's difficult because different sources, so we have heart models in your lab exam, APR, and diagrams from your text, they all may be slightly different, although I will say the large bulk of vessels will be coming from the APR for your lab exam for those of you in lab that are listening. And I'll try to mention a little bit more about ECG in the lab later tonight, but I do want to spend some time here making sure everyone kind of gets this. There are hundreds of questions about this. There are only so many ways to ask those questions. And so you can see that it's going to be pretty detailed, and maybe you may get very similar questions since it's a random pulling from the computer. You may get 3 questions about valves opening and closing. I hope not, unless you really know your valves well. But just know that that's a possibility, and it's unfortunate just by the virtue of how the computer is randomly picking those. So you may get one emphasized more than the other, but I promise you'll get several cardiac cycle questions because of the amount of questions in the banks that are dealing with this right now. And then, of course, the only other chapter you had was blood, and so you can imagine blood's going to be pretty specific too as far as those questions. But it is weighted, if you've noticed in the notes from instructor, it is weighted more on chapter 20 because you spent 2 weeks on it versus the 1 week in blood. So this is where really to focus your attention. All right, so as you can see, this is actually several graphs put together in one, and they did this for two reasons. One, to make it more confusing. Just kidding. One, to give you an overall picture, I think is one of the reasons they did that. And two, it also gives you, allows you to see what's individually happening for each section that we're trying to deal with or trying to understand and learn about. And so rather than give you 5 diagrams and then have you put it together, they've kind of put it together for you. So we're going to start from the top and go downward. Now we talked about an ECG last week. The ECG is an electrical conduction of the heart, and is only that electrical activity, so the depolarization and repolarization of those membranes in the atria and in the ventricle. If you recall, there's I mentioned in your quiz, you'll probably find these too, that there are several questions that talk about contraction. Contraction, it's kind of a key word to know. Oh, probably none of the above, because it's electrical stimulation. It's depolarization of the atria here, depolarization of the ventricle here, and repolarization of the ventricle here, with the repolarization of the atria once again getting lost in the QRS. Now, I want you to notice that you see that this does happen before the actual contraction. So here's the contraction right here. There's a contraction, the isovolumetric contraction of the ventricles. And so you can see the electrical activities beforehand. The actual, the actual contraction of the atria actually starts right about here, right about middle here with this P. You can see that as the volume up here starts to increase. So the electrical activity happens slightly before, and then the contraction happens. Contraction of the atria, contraction of the ventricles right here in this blue part. And then relaxation of the ventricles happens right here. And the relaxation of the atria actually happens here as the blood's being ejected. Okay. So relaxation, repolarizations here, relaxation of the actual muscles here of the atria. All right. This next one has to do with pressure. Now, when we talk about pressure, when we talk about blood pressure, and we'll talk about blood pressure more next week when we start talking about the circulatory system, we're specifically talking about the pressure of the ventricle as far as this black line goes. So this black line here is the pressure of the ventricle. The little dotted red line is a pressure at the aorta. Okay, and that's important to note. It follows very closely what happens with the pressure of the ventricle, which makes sense because the aorta is that one main vessel that comes out of the left ventricle. The right ventricle, as we've discussed, the right side doesn't have it's not as big of volume or mass, I should say, of skeletal, of cardiac muscle, and it only has to go to the lungs, so it doesn't need the strength of contraction that the left ventricle does. And so you actually see that the pulmonary arteries right here in blue are much lower in their pressure. They still kind of follow the same line, but it's a little bit lower. And that's not as important. We don't really focus a lot on that, but we do focus on the aorta a lot, and you'll see that as we get closer down. But that's what those pressures are, and you can see that you get a little bit of pressure of the ventricle as the blood gets rushed in. So here during atrial systole, which is contraction of the atria, you're going to get an increase in volume because it's going to push the little bit of blood that isn't been collecting in the atria into the ventricle, and so you get a little bit of an increase of pressure. Well, then you have what we call this isovolumetric contraction, which means all the valves are closed. It's a closed container. So imagine a balloon that you've filled and tied, and then you start squeezing on it. The air inside is going to increase the pressure dramatically, and we see that here. Oh, come here, green arrow. We see that here. We see this big increase of pressure. And as it gets so much so that the pressure exceeds what the valves can hold on to, so the valves actually are forced open, and the blood's ejected. And as the blood's ejected, you're having that main force of contraction. So that's why this ventricular pressure still increases even though blood is leaving, because of the fact that it's in that contraction phase. And as the blood does leave and we're getting close to finally the final contraction, we start to see a decrease in pressure. And then the valve closes. Again, the valve to the aorta and the valve to the pulmonary arterial trunk, those semilunar valves close. And you have relaxation of the muscle. So when you have relaxation of the ventricle muscle, the pressure is going to go down quite a bit. And then the valves open and the heart starts to fill again, valves close, etc. So in this particular pressure, remember this is black line as the ventricular pressure, specifically the left ventricle pressure. But what you'll see is that we have a point where the valves are open and then the valves are closed. Okay, and notice that that's that period of ejection. The valves open when the blood's finally forced through, and the valves close in order to prevent backflow when most of the blood has left. Now, under rest, normal ejection fraction is about 70-75%. So there's still blood in the ventricle. So you'll see that down here. But we do start seeing a drop in pressure, and then we see a dramatic drop in pressure as the ventricles contract, but there's no blood coming in because all the valves are closed. And then finally, the valves open again. We have low pressure until it's time to push more blood in. Okay, so pay attention to when the semilunar valves open and the semilunar valves close. The AV valves close, so the valve between the atria and the ventricle close once again to prevent backflow. So they're going to close after the atria has contracted, and then the atria will relax while the ventricle starts to contract. And you'll see the AV valves open again at the end of isovolumetric relaxation. So during this period of isovolumetric contraction and this period of isovolumetric relaxation, all the valves are closed. So during phase 3 and phase 5, according to your text, the different phases that they talk about, all valves are closed during those isovolumetric contraction. Iso means same. Volume, you know what volume means. So that's once again a contraction where it's a closed system like a balloon with its thing tied off. And then relaxation the same way, where you move your hands away from the balloon and allow that air inside to expand again, or that space to expand again. All the valves are still closed. It would be the equivalent of squeezing the balloon so tight that you force that little knot open and let all the air out, essentially. As far as the pressure here that happens to force the semilunar valves open. But it's really important to know when the valves are open and when the valves are closed. Okay, and we kind of see that here in this pressure of the ventricle. All right, let's go down to the left ventricular volume. And once again, we really just focus on the left. The right is much more relaxed in the sense that we don't see the same pressure changes because we don't have the same muscle mass in the right ventricle as we do in the left. So whenever we do a volume or a pressure, we're really just talking about the ventricular volume. And the same when we talk about blood pressure. When we're talking about blood pressure, we'll learn in the next week or two, we're relating it to the pressure at the aorta. And so that's why the closer you get to the aorta you can. So we're measuring just the pressure in the arteries. There's literally no pressure in the veins. And so when you see anything that has to do with blood pressure, know that that's trying to extrapolate the pressure that's at the aorta. And this is, once again, that aortic pressure that you're seeing here in the red dashes. Okay. Once again, in atrium area, though we don't really pay much attention to because it is so low. So left ventricular volume. Notice that at let's go over here at the beginning of diastole. So we just relaxed the ventricle. Notice it still has about 55 milliliters of blood in it. So it isn't completely emptying, which is actually an advantage when we're in exercise or in situations that are stressful or we're highly sympathetic stimulated, that we can have a greater force of contraction. We can force more blood out than normal. So rather than 55, maybe we'd only be left with 35. You get a closer to 85 to 90% ejection fraction. So most of the blood that's in the ventricle will be pushed out. At rest, once again, is about 70 to 75%. So when we relax the ventricle and it's starting to fill, notice it has a good increase. The valve is open, the AV valve open, so blood flows into the atria and also into the ventricle. And that's one thing that a lot of anatomy and physiology students, I guess, you don't really think about it. That the valve's open. We always teach that the atria contract and they push the blood in the ventricle, but actually that valve's open the entire time, so we get a good amount of volume filling the ventricle, and we actually need that valve to be open. Otherwise, the atria couldn't hold enough that we actually need to propel to the body. And then at the end of diastole, so the end of rest, so to speak, the AV valve closes. There's a slight contraction, and it pushes open and adds. So right here, there's that contraction of the atria, pushes a little extra blood into the volume. Once again, we have an isovolumetric, so the volume stays the same as the ventricle contracts, and then the ventricle pushes out the blood, and you decrease that volume. And then once again, once the valve's open, you start increasing. So the left ventricular volume diagram is just simply showing how we really get the blood out of the ventricle, get the blood in, atria pushes a little more in. These flat little plateaus are when we're in contraction and relaxation mode of the cardiac muscle. And that is another phase of the cardiac cycle. Now, well, that's another faction. I've got to be careful because your book calls these time periods phases. So it's another faction of cardiac function that we need to know, is the volume and how it changes. And finally, this diagram has your heart sounds. Now, your heart sounds correspond to your valves closing. So you would anticipate with the AV valves closing here prior to an isovolumetric contraction, that's your first sound, is the AV valves closing. They close to prevent backflow of the blood into the atria. The second heart sound is those semilunars closing right here. Is when that sound begins, because it also wants to prevent backflow into the ventricle from the blood that's being pushed into the aorta. Now, occasionally we'll hear a third heart sound. This is typically related to or corresponds to the flow of blood into the ventricle again. And some people believe that, you don't necessarily hear that a lot. If it is, it's a very soft, swooshy sound. Or unless you have other problems like leaky valves, and then you might hear different sounds. But the third heart sound is left there because it is attributed to, once again, that rush of blood into the ventricle. And you can see it's just right there as it's starting to fill up. So when you take all of this into consideration, at any given time period, you should be able to determine if the valves are open or closed, if the volume is high or low, if the pressure is high or increasing or decreasing, what the electrical activity is, and how that corresponds to the heart sounds. And so that's what this diagram is about. Now, as I mentioned, your book calls these time periods phases. There's 5 of them. There's a lovely table on table 20.2 on page 686 and 687, which I can't show you because, as I've mentioned before, McGraw-Hill doesn't give us access to the tables. I can get all the figures I want. I can get all the animations I want, although I can't get them here for some reason. I can't get them to play once I bring them in here. And if I show you my screen, then they make it really small, although it's just the weirdest thing. I don't know if that's an Adobe Connect thing or if it's a McGraw-Hill protecting their stuff thing, but I have all access to that, but I don't have access to tables. So if you look at table 20.2, it gives you each of these things that are happening. It has your time period, which this is kind of a hard thing because it is a time frame here, but it's difficult to really understand because if you think lub-dub, that's a pretty quick, this is happening fairly quickly, especially if you're running, right, and your heart rate's running, 150 beats a minute. That's, less than, or that's more than 2 a second. And so you can see how it feels like it's taking longer than it really is, but it does go quickly. Anyway, it gives you a time period. It gives you the valves, where the valves are, ECG, pressure. And like I said, don't worry too much about atrial pressure. Just kind of remember that the pulmonary trunk and the atria are much, much lower. We don't really see a change in pressure there. volume's important, and then your heart sounds. And it goes through each phases and so, or periods, and so it talks about period 1 being the passive ventricular filling. This is where the blood is filling both the ventricle and the atria. The valves are open. There isn't any stimulation at this time. And notice that's that interval between depolarization of the ventricles, and they're just near the beginning of the beginning of the depolarization of the atria before we get into active ventricular filling, which is the second time period. The active is the fact that we're actually contracting the atrial muscle in order to propel or push a little bit more of the blood into the ventricle. The third period is the period of isovolumetric contraction, once again where all the valves are closed and you're contracting that muscle, creating a large amount of pressure inside the ventricle, eventually that will cause the semilunar valves right here to open. So, we're going from here to here in pressure, causing the semilunar valves to open. And as it still continues to contract and ejects the blood, that's why it's called period of ejection, we see a large increase of pressure still, and as then finally that's winding down, the valves will shut to prevent backflow, and then relax, decreasing pressure dramatically, then opening it up again. So once again, this is just kind of a overview between your table and your figure, and even fundamental figure 2018, which let's go ahead and show you that now. This one also kind of just shows you in the heart what's going on, and maybe gets a little bit, maybe gives you a little bit better feel for what's happening in the heart itself. And so if this confuses you, then don't look at it, because it does. I've had some students say that this made it worse, but they prefer the other table and figure. But it just is showing you this active. See here, it starts with the active ventricular filling, once again, where it's starting to contract the atria on either side. The AV valves are open, pushing the blood in. Semilunars are closed because there's no reason for the blood to leave at this time. We want all the blood to leave together. And then the isovolumetric contraction, where all the valves are closed. Period of ejection, where it's pushing through the aorta there and the pulmonary trunk there. The semilunar valves are open. The AV valves are still closed. They don't open up again until after the period of isovolumetric relaxation, when all the valves are closed again, and then they open up. And the semilunars also stay closed. So you notice that the semilunars are only open during phase 3, and the AV valves are only open during phase 5 and 1. So during that filling phase, and once again they've divided it into 2, but the AV valves will stay open until the end of ventricular filling, and then they'll close up. Okay, so there's only a little short thing, and that actually leads me into what I also sent to, or what I also attached for you. And some students find this really hard. Other students find it really helpful. If you find it hard, then don't look at it. Honestly, it's just meant to help. So if it confuses you more, then don't worry about looking at it. But this is a very rough diagram trying to show you once again these phases, and only related to pressure and volume. Nothing to do with time here. And that's where some students find it difficult. Other students find little aha moments, and that's why I still include it, because I've had students tell me it's really helped them with their comprehension. But it's just the pressure related to the volume, once again, left side of the ventricle. And this is just trying to take a couple of those diagrams, separate diagrams, and try to show them to you together. So we see that the phase 1 is here, the phase of ventricular filling, both passive and active. So, 5 and 1, I guess you could say. So this is 5, and then right about here we see 1, where we have the atria contract and push a little bit more in the volume, so the volume goes up. Okay. At this point in time, the AV valves close, and they stay closed until the beginning, again, of phase 1. Isovolumetric contraction. The semilunar valves open. AV valves are still closed, though. And we see a little bit of increase of pressure once again, but then eventually as the volume starts to drop, we see a small drop in pressure, and we saw that in the other diagram. Semilunars closed, AV valves are still closed, isovolumetric relaxation, AV valves open. So this, you can relate those three at least fairly easily. Volume, pressure, valves. Heart sounds, you know, correspond. So when the AV valves close here, first heart sound. Contraction, open and close, second heart sounds right here. So you can see that, once again, there's no time involved in this particular diagram. And so lub, dub, lub, dub. Oh, sorry. Yeah, dub. There, because they open up again here. All right, so that's just another thing. Like I said, some students find it helpful, some students do not, but I just wanted that to be available to you as well, if that helps. Some people have anything visual or anything they can kind of wrap around seem to like. So that's that. If you have additional questions, you know you're welcome to email me at any time at all. Okay, let me stop that here. So, does anyone have any questions at this point in time? I would like to go over a little bit in lab, but I would like to go over the end of chapter 20 a little bit if there aren't any questions. But I want to make sure that for the most part that seems to be okay. And make sure that your terms, you understand that systole is the period of contraction, diastole is that period of relaxation. So, okay, great, Whitney. So make sure you understand that when we talk about, what is that? I don't think it's this week. It might be next week. No, it's not next week. You're studying for your exam next week. That sometimes people get a little confused about what is systole and, oh yeah, so it is this week in lab. Systole and diastole, you know, we're talking about contraction and relaxation phases. And so please make sure you know systole is contraction phase, diastole is relaxation phase. When we talk about systolic pressure and diastolic pressure, which is slightly different than systole and diastole, systolic pressure is the pressure of the ventricle and or aorta. As you know, if you recall, they're pretty similar. Let's look at that again. Oops, here. See, they're pretty much right on board with each other all the way around, aorta and ventricle. So when we talk about systolic pressure, see, here's, see, it's already labeled. Systolic pressure is the highest pressure that the aorta gets as the blood is pushing out. Diastolic pressure is the pressure that we see. I don't think it shows it. Let's see, down, down, down. Oh, red, 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 red. Diastolic pressure right here. It would be the lowest point of aortic pressure we have prior to contraction. Of course, that would be prior to those valves opening and pushing out the blood. Okay, because as they close and preventing backflow, there's still going to be a little bit of blood there to cause pressure until it's all been pushed out to the body. So diastolic pressure is the pressure at the aorta that corresponds to the pressure of the ventricle at the end of rest, or the lowest point we see. Systolic, the highest point, or at the height of contraction. And the difference between those is pulse pressure. All right. You will have, if let's see. I know a large part of it is, oh yeah. Okay. So we used to have this as a question, but we don't anymore. So, but it may show up in your exam. It's actually more detrimental to have a high diastolic pressure than it is to have a high systolic pressure. So if your pressure is high here, your muscle can still relax. It's just under more stress and strain. But if your resting pressure is high, then that puts a lot more workload on your heart. And so know that having a high diastolic pressure is more dangerous physiologically, health-wise, than a high systolic pressure. Of course, if this is high too, that's a problem. Yeah, just a second, Jane. So, no, like I said, systole and diastole. As far as the ECG charts where heart function is compromised, it's giving you some examples on figure 2017 of how you can use an ECG to find out that there are problems in the heart. And they give you some examples. I'm not an ECG technician, and a lot of these have to do with, you know, the type of lead and so forth that you have. But you can see, for example, and we kind of talked about this last week, but let's review it again, because in your lab, for those of you that have lab, whether with me or Brother Parkinson, if you're taking it online, Lab has a video of several, and you need to pay attention to those because those are on your exam, third exam. I know that's a little ways away, but lab, abnormal ECGs are important to kind of understand, and it's converting it, so let's just hang on for a minute. Okay, maybe. I didn't think it would take this long. Need to have that little round spinner of death that when you're in an apple that's telling you that it's never going to happen. Anyway, so Jane, for example, if we can get this to upload, I'm still going to wait for it to convert. Maybe it will by the time I finish talking. But for example, when we are in a fibrillation state, yes, it's posted on the notes or lectures from Sister Foster, cardiovascular part 1. So on your fibrillation, when we talked about that before, it's where you don't have a congruency between the atria contraction, if it's atrial fibrillation, or ventricular contraction. So instead of contracting all at once as one whole unit and unify it and pushing the blood out properly, in a fibrillation state, you're getting excitation all over the ventricle and all over the atria. So they're little bits of cardiac muscle are contracting all at the same time, so you don't get any real blood pushed out. It can be very, very obviously detrimental very quickly. But oh my land. Okay, let's just cancel that. Try it again. Share document. Let me try to see if I can find it from before. So 2017. Okay, let's see if it'll work this time. Oh, did not like that one. I tried to do that. Hang on. Oh yeah. Usually it pops up really fast. I'm not quite sure why it's. I'm always happy when this happens as I'm recording, but I'll try it again. Okay, here we go. Oh, maybe not. Anyway, as you can see in ventricle, if you're looking at your book, in ventricular fibrillation, there's nothing happening. There's no real nice waves of P or QRS because it's happening randomly throughout the heart and in little bits, and so you don't see good depolarization or repolarization. And the same with atrial fibrillation. You still have the ventricles contracting at once, but they're not getting, and so you have QRS, but because, oh, there we go, finally. But you're really not getting normal QRS complexes because the atria, if you recall, it goes from the SA node to the AV node, and then from the AV node through the interventricular septum, so through the bundle of His, and then out through the Purkinje fibers. So if that is not being stimulated properly, the signals from the SA node to the AV node is going to be affected. It's also going to affect how the QRS, how the depolarization is happening. So you don't get a very strong contraction because you're getting a delay, or you may get one happening and then another happening. So there are, because it's not in complete fibrillation, the ventricles, you're still going to see QRS complexes, but it's going to happen pretty quickly if that electrical signal doesn't happen very well. A bundle branch block, if you think about where that is, okay, so the ventricles aren't getting all of the depolarization and repolarization at the same time, you're going to see QRS looking funny too, because it's going to take longer with that block for everything to repolarize, that type of thing. Premature ventricular contraction. So you don't see a P wave. In other words, the ventricle's contracting before the atria. So you're not going to really see P waves. You're going to be kind of funky. You're going to be a weird contraction issue because you're not getting the complete depolarization. So that type of thing is just showing you those different types that can happen. But if you have lab, focus on the video in the lab that shows the different ones. I think it shows 3 or 4, and the terms that correspond to those. Now, the other thing I wanted to mention about lab, for those that are listening later and for those of you that are here, I get this all the time. You get to see on a video how to make an electrical access assessment, as far as how you count up the squares and count down the squares, and you kind of add everything together to get a net value, which then you can use on a little graph. I'm pulling up my graph now. That gives you an idea of what degree the lead is and what the electrical access of this particular heart is, which can give individuals much more qualified than I, a cardiologist, an indication of what's really happening there. One thing that happens often in this lab is that people don't recognize that the PDF that they get is 3 pages long. So it's kind of funky. It's like your syllabus. Unless you download it, sometimes you end up bypassing. I don't know if it's the way Dropbox is working or what, but anyway, download the PDF. Notice that you have 3 pages. You have lead 1 and lead 3, and it's those combination of values that then give you the cross section on the 3rd page to draw and get your angle. Now, we get angles all over the place, but I will tell you the correct one is much closer to, I'll just give you a range, the 80 to 100 range. But you know, you need to be a little bit narrower, sorry, I have a hard time speaking, than that to get full credit. And oh, that's why my water's way over on my table, on my office, a table on the other side. I was like, oh, I feel thirsty and I can't talk. So that's probably why I haven't been having any water. Anyway, so don't forget to really look at that. And then if your value's off, like if you get 60 degrees because you're just going by the example, you won't get it right. So make sure you do it yourself. The ECGs lead 1 and 3 that they give you to figure out are different than the example. I have a lot of students that just write 60 degrees because that's what the one was, the practice one was. So if you haven't looked at lab yet, it's not so bad. It's all about ECGs and how you just describe it, how you set somebody up. Once again, we talk about diastole and systole. Oh, and it has a wonderful question that makes you think about what changes the most, systole or diastole, as the heart rate increases or decreases. So think about that. That's actually a really good question. And then once again, it gives you a coordinate axis to calculate, and then another question to think about. If someone's lying down, what happens when they stand up? What direction does the heart electrical axis orient more? Is it more horizontal, more vertical? Is it upward? Or frontward rather, forward or backward, that type of thing. Okay. So, any other questions? Exam opens up this Thursday. It closes next Tuesday. The breakdown as far as how many questions from each week and the reading guide that's kind of all squished together so you can use it as a study point is in the notes from instructor. And yeah, I think that's it. So if you don't have any other questions, we are free to go. If you do, I'm happy to stay. In the meantime, if you get questions, you're welcome to email me if you have questions about the lab. Peyton, I still want to say my last TA's name from last semester, Peyton, will be having her sessions. If you attend a session and kind of interact and ask some questions, you should be getting extra credit points, 1 per session up to 8 points for lab. If you're not seeing that, email me and I will make sure it gets done. Any other questions or any other thoughts or comments or anything? Melissa, Jane, Whitney's typing, but no, you're welcome. Thank you for coming. It's always easier when I have an audience, even if you don't type anything. Good, I'm glad. All right, 23. Yeah, let's go to that. Critical thinking. Do you have, hang on, let me find it. You're in chapter 20, right? Let me just get to it. View and comprehension. Okay. Am I in the wrong chapter? I only have 11 critical thinking problems, Whitney. Okay, well, review and comprehension. Okay. Oh, you scared me to death. I'm like, I don't know where she is, and that kind of concerns me. All right, let's see. 23. Because of the baroreceptor reflex, when normal arterial pressure decreases, all right, so, baroreceptors are stretch receptors. So if normal arterial pressure decreases, you're going to see what happening to the frequency of the baroreceptors. Are they going to increase? Are they going to decrease? Are they going to affect something else? No worries. I want you to think about that. So baroreceptor stretch reflex. So if it's saying if normal pressure decreases, what happens to the amount of stretch in the vessels? Does it increase or decrease? And you, Melissa, you can type that in too, either one of you. Good, it's going to decrease. So if it's decreasing, what kind of action potentials are you going to get? Yes, okay. And subsequently, if we have less action potentials, the pressure's decreasing, you may not necessarily decrease your heart rate because you have a basic heart rate. We really only decrease the heart rate with parasympathetic stimulation, not with stretch reflexes. Stretch reflexes, though, if it gets really stretched, can then stimulate sympathetic to help increase. But stroke volume decreases. We also, once again, you have a base with rest, and then it's saying cardioregular center stimulates parasympathetic neurons. The lack of stretching wouldn't necessarily do that, because stretching, if you recall, that baroreceptors and chemoreceptors are kind of that immediate local control, I guess we could kind of call it that, and then sympathetic and parasympathetic's more overall systemic control on the heart, taking, more than a moment-to-moment type of reaction. Yeah, and so the best answer is C, but I think it tries to confuse you a little bit, but remember the purpose of those receptors versus the purpose of, so regulation of the heart happens in various levels. Like I said, some of it's just kind of a moment-to-moment thing, others a little bit more systemic, and then of course finally the hormone system, the endocrine system, hormones will help longer term do one thing or the other. Okay, all right. Any other questions? Oh, I'm still recording. I should probably stop. Stop.